Hello, in this lecture I will explain you what is mathematical induction. Mathematical induction is a logical method to prove that a statement, a claim or an equation is true for all the natural numbers. A natural number is a positive integer like 1, 2, 3, 4, 5, 6, 7, etc. And actually, if we want to prove that a statement is true for all the natural numbers, we actually must do two stages. The first stage will be to check if the statement is true for n that equals to 1, and only if we passed that test, that is to say only if the statement is true for n that equals to 1, then we will proceed to the next step, that will be the next stage. And in the next stage, actually, we will assume that the statement is true for n, and we will prove it for n plus 1. Okay, so we will create the first expression or equation for n. That is to say, it will be the induction's assumption or induction's hypothesis, and then we will make the second equation or expression for n plus 1. And the expression for n plus 1 is the equation that we will have to prove that it is true, and we will prove it when we rely on our assumption that the first equation is true. The equation for the statement for n is true according to our assumption or according to the induction's hypothesis, and when we rely on that assumption, we will prove that the second equation for n plus 1 is also true. And actually, in this way, we proved that the statement is true for all the natural numbers. Okay, now I will explain what is the logic behind the mathematical induction proof. You should remember that in the first stage we proved, or we checked, that the statement is true for n that equals to 1. So we know that the statement is true for n that equals to 1. And then in the second stage, we proved that if the statement is true for n, then it must be true for n plus 1. So now we know for sure that the statement is true for n that equals to 1 because we checked it, that it is true, and it is indeed true for n that equals to 1. And according to the general proof that if it is true for n, that it also must be true for n plus 1. So the statement must be true also for 1 plus 1. That is because n equals to 1, so the statement also must be true for 1 plus 1, that is 2. According to our general proof that if it is true for n, it also must be true for n plus 1. So now we know that the statement is true for n that equals to 2. So we will repeat on the same process in order to prove that it's also true for n that equals to 3. And we will prove that it's also true for n that equals to 3 because we know that it is true for n that equals to 2, and it also must be true for 2 plus 1 according to our general proof that if it is true for n, it also must be true for n plus 1. Now n equals to 2, so it must be also true for 2 plus 1. That is to say, it must be true also for 3. And then when we know that it is true for n that equals to 3, we will repeat on the same process in order to prove it that it is also true for n that equals to 4. Exactly in the same way we will say that now we know that the statement is true for n that equals to 3, and because of our general proof it also must be true for 3 plus 1, because now n equals to 3, and it must be true also to n plus 1, that is 3 plus 1, that is 4. And then we will prove it for n that equals to 5. Okay? Okay? In the same way, we will prove that it also true for n that equals to 5. And after we prove it for n that equals to 5, we will prove it in the same way for n that equals to 6, and so on and so on. So in this way, we actually proved that the statement is true for all the natural numbers. Okay, so in order to clarify the topic, I will give you 2 examples. So we will start with the first example. One plus 2 plus 3 plus n equals to n times n plus 1, all divided by 2. So we want to prove that this statement is true for all the natural numbers. 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So we will start with the first stage, that is to say we will check if the statement is true for n that equals to 1. So in this side of the equation we will have only 1 because n equals to 1. 1 equals to n times n plus 1 divided by 2. N equals to 1, so it is 1 times 1 plus 1 divided by 2. This equals to 1 times 1 plus 1 is 2, divided by 2. 1 times 2 is 2. 2 divided by 2 equals to 1. So 1 equals to 1. So we passed the test, and we actually showed that this statement is true for n that equals to 1. So now we can move to the second stage. That is to say, we will assume that the statement is true for n, and we will prove it for n plus 1. So we will create two equations. The first equation will be the induction's hypothesis, that the statement is true for n. So the expression for n will be 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So this is the induction's hypothesis of the induction's assumption. We assume that the statement is true for n, and when we rely on that assumption, we will prove that the statement is true for n plus 1. So we will write the expression for n plus 1, and we will prove that it is true, that this expression for the statement's expression for n plus 1 is true. So the expression for n plus 1 will be 1 plus 2 plus 3 plus n plus n plus 1 equals to n times n plus 1 divided by 2. The expression for n plus 1 is actually in this side of the equation. We have n times n plus 1 divided by 2. So wherever is written n, we will write n plus 1, because we want the expression for n plus 1. So it will be n plus 1 plus 1 all divided by 2. Okay, so n times n plus 1 divided by 2. We replace n by n plus 1 because we want to the expression for n plus 1. So wherever it is written n, we will write n plus 1. So here is n, we will write n plus 1, and in the brackets we have n, so we write n plus 1. Here is n plus 1, so it will be n plus 1 plus 1. Okay? So So it is n plus 1 times n plus 1, all divided by 2. So we know that n plus 1 is n plus 2, so we will write it down. So the expression for n plus 1 that we have to prove is 1 plus 2 plus 3 plus n plus 1 equals to n plus 2 times n plus 1 divided by 2. Now if we assume that the first equation for n is true, and when we rely on this assumption, we have to prove that the expression 2 for n plus 1, or equation 2, is true. So in order to prove that equation 2 is true, we should look on this expression. This expression is exactly the same, is identical to this expression, but this expression in the green color equals to n times n plus 1 divided by 2, so we can substitute 1 plus 2 plus 3 plus n by n times n plus 1 divided by 2. Okay, so we'll do it now. One, 2 plus 2 plus 3, and so we substitute 1 plus 2 plus 3 plus n by n times n plus 1 divided by 2, because they equal to each other, so we can substitute them. We can substitute one by other. So 1 plus 2 plus 3 plus n equals to n times n plus 1. Here we have n plus 1, so we will copy it as it is, equals to n plus 2 times n plus 1, all divided by 2, so we'll copy it as it is. Okay, so actually this is the expression or the equation that we have to prove when we rely on the assumption that the first equation is true for n. That is the induction hypothesis. So in order to prove that the second equation is true, we will divide both sides of the equation by n plus 1, because we have n plus 1 in both sides of the equation. So we'll get that n times n plus 1 divided by n plus 1 equals to n. We divide it by 2, and n plus 1 divided by n plus 1 equals to 1, and n plus 1 times n plus 2 divided by n plus 1 is n plus 2, or divided by 2, and So as you can see here, n times n plus 1 divided by n plus 1 is n, we divide it by 2, n plus 1 divided by n plus 1 is 1 equals to n plus 1 times n plus 2 divided by n plus 1 is n plus 2 and we divide it by 2. So here we can separate this expression to two parts. It will be n divided by 2 plus 1 equals to n divided by 2 plus 2 divided by 2. Okay, after we separated this expression to two parts, then it will become n divided by 2 plus 2 divided by 2 equals to n divided by 2 plus 1. We copy this expression as it is, and 2 divided by 2 is 1, so we can write it down. So we got here identification, n divided by 2 plus 1 equals to n divided by 2 plus 1. So we actually proved that the second expression for n plus 1 is true. Okay, this is the second expression, and we proved that the second expression for n plus 1 is true. So we actually proved that if the expression of the statement is true for n, then it must be true for n plus 1. Okay, so in this way, as I've already explained to you, we actually proved that this expression is true for all the natural numbers. Okay, and I have already explained to you why it is true for all the natural numbers, so I will not repeat on that explanation. Okay, and now we actually will move to the second example. One to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square, all divided by 4. Again, we must prove that 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square, all divided by 4. So we'll start with the first stage. That is to say, we'll check that this statement is true for n that equals to 1. Okay. Okay, so n equals to 1. In this side of the equation we will have n to the power of 3 equals to n squared times n plus 1 square all divided by 4. So n equals to 1, so it will be 1 square times 1 plus 1 square divided by 4 equals to n square, 1 square is 1, 1 plus 1 is 2, so it is 2 square all divided by 4 equals to 1 times 2 square is 4 divided by 4, so it is 4 divided by 4 equals to 1. 1 to the power of 3 is 1 equals to 1. So here we actually passed the test and we actually verified that this statement is true for n that equals to 1. So we passed the first stage. Now we will proceed to the second stage. That is to say, we will assume that this expression is true for n, and when we rely on this assumption, we will prove it for n plus 1. Okay, so the induction hypothesis will be that the statement is true for n. And the statement for n is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square all divided by 4. So actually equation 1 is the induction hypothesis or induction assumption. We assume that equation 1 is true, and when we rely on this assumption, we will prove that the expression or the statement, our statement for n plus 1 is true. So we will have to prove that this statement for n plus 1 is also true. So the statement for n plus 1 will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals so now we have to write the expression for n plus 1 and to prove that the expression for n plus 1 is true. So the expression for n plus 1 will be 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus plus n to the power of 3 plus n plus 1 to the power of 3, because the expression is for n plus 1, so we will add numbers until we arrive to n plus 1, and it includes also the n plus 1 to the power of 3. Okay, so all equals in the original expression we have n squared times n plus 1 squared all divided by 4. So because of the fact that now we create the expression for n plus 1, so wherever it is written n in the original expression, we will write n plus 1. So instead of n squared, we will write n plus 1 squared, and n plus 1 squared will become n plus 1 plus 1, because instead of n, we will write n plus 1, and it is in the original expression plus 1, so we will add 1, and all squared, and we divided it by 4. So n plus 1 plus 1 is n plus 2, so we will write it down. So we actually copied this line here, and the only change that we made is that instead of n plus 1 plus 1, we wrote here n plus 2, because n plus 1 plus 1 equals to n plus 2. So all of the rest part, all the other parts is the same. And again, we will repeat on the same process as we did in the first example. If we look on this part of the expression, that it is in the green color, this part equals exactly to this part, is identical, and this expression equals to this. So we can say that this expression equals also to this, because they are equal to each other. So we can say that we actually substitute 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 by n squared times n plus 1 squared all divided by 4. We can substitute one with each other because they are equal to each other. So instead of 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3, we can write n squared times n plus 1 square divided by 2 plus n plus, so we substituted this expression by n squared times n plus 1 square all divided by 4, and then we'll copy what is written here. So we'll copy n plus 1 to the power of 3 equals to n plus 1 square times n plus 2 square all divided by 4. So the only thing that we changed from this line to this line is we substituted 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 by n squared times n plus 1 squared divided by 4. We substituted it because they're equal to each other, and we copied the other parts of the equation. So we must prove that the second expression is true for n plus 1, as we rely on our assumption that the first equation is true. Okay? The first equation is the induction hypothesis. We assume that the expression for n is true, and we will have to prove the expression for n plus 1 when we rely on our assumption that expression 1 is true. Okay, so here, in order to prove that the second expression is true, we will divide both sides of the equation by n plus 1 squared, because we have n plus 1 squared in both sides of the equation, and we will get that n squared times n plus 1 squared divided by n plus 1 squared will be n squared divided by 4 plus n plus 1 to the power of 3 divided by n plus 1 squared will be n plus 1, and n plus 1 squared times n plus 2 squared divided by n plus 1 squared will be n plus 2 squared divided by 4. Okay, so we will have to prove that this expression is true. So we will multiply both sides of the equation by 4. Okay, we multiplied both sides of the equation by 4, and we got that n squared divided by 4 times 4 is n squared, plus n plus 1 times 4 is 4n plus 1, and n plus 2 squared divided by 4 times 4 is n plus 2 squared. So now we will open the brackets. We get that n squared plus 4n plus 4 equals to n squared plus 4n plus 4. So after we open the brackets, we got that n squared plus 4n plus 4 equals to n plus 2 squared is n squared plus 4n plus 4, according to the formula that a plus b squared equals to a squared plus b squared plus 2ab. So we got here in identity. So in this way we proved that expression 2 is true, or we actually proved that if the statement is true for n, it must be also true for n plus 1. Okay? And actually in this way we proved that this statement is true for all the natural numbers. Okay, so we actually can summarize the topic of mathematical induction and say that mathematical induction is a logical logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. And the natural number is a positive integer like 1, 2, 3, 4, 5, etc. And we have two stages in the mathematical induction. In the first stage, we will prove that the statement is true for n that equals to 1, and only when we pass the test and it indeed true for n that equals to 1, then we will proceed to the second stage. That is to say, we will assume that the statement is true for n, and then we will prove it for n plus 1. So in this way we will create two equations. The first equation will be the induction's hypothesis that the statement is true for n. So we will create the expression for n, and we'll assume that the statement is true. And when we rely on this assumption, we will prove that the statement is also true for n plus 1. And if we succeeded to prove that the statement is true for n plus 1, so we actually proved that the statement is true for all the natural numbers. Why? Because in the first stage we proved that the statement is true for n that equals to 1. And then in the second stage we proved that if it is true for n, it must be also true for n plus 1. So now we know that it is true for n that equals to 1. So it also must be true for 1 plus 1, that is 2. And now that we know that it's true for n that equals to 2, and we also proved that if it is true for n, it also must be true for n plus 1. So we know that it is true for 2, so it also must be true for 2 plus 1, that is 3. And we will proceed in the same way, and we will prove that it is true for 4, for n that equals to 4, and so on and so on. And in this way, actually, we proved that the statement is true for all the natural numbers. Okay? Thank you very much.